Hello Slifox community! In the previous project we demonstrated how to set up GPIO for STM32 and used a push button to control 3 LEDs. And the link to the playlist is provided below in the description. This time, again, we are going to set up GPIO, but with a different electronics component. 7 segment. 7 segment is nothing but 7 LEDs gathered together in an arrangement to represent number 8. Thus, by using this arrangement, you could show all numbers from 0 to 9. These LEDs are accompanied by another LED for lighting that dot in the right down corner of the 7 segment. It is used for decimal numbers. Just as a reminder, note that LED is a specific kind of diode, and diode is on whenever the voltage of its anode is higher than the voltage of its cathode. We've got two kinds of 7 segments: common cathode and common anode. In common cathode 7 segments, the cathode of all segments are connected together, and these pins are connected to a pin which is always in the middle of the both top side and bottom side of the 7 segment. And the anode of each segment is connected to different pins of 7 segments, as you can see in the images. On the other hand, in common anode 7 segments, the anode of all diodes and LEDs are connected together, and they are connected to the pin which is in the middle of both top side and bottom side of 7 segment. So these pins are connected internally, and when you are preparing the circuit, you don't need to connect these two pins together. And cathode of each segment is connected to different pins. But how to know whether our 7 segment is common cathode or common anode? We will learn it in a second. Prepare your multimeter. Set it on diode mode. Connect the red probe to the port which is related to voltage, resistance and frequency, and then connect the black probe to the common port. Then prepare your 7 segment, and you can see that when these probes are connected together, they produce a sound. I want to say that they beep. And I connect the red probe to one of the common pins, and then connect the black probe to any pin. You would see that the LED of one segment is turned on. It doesn't matter which pin you connected. It turns different LEDs on. For example, here it turned the dot on, then it turned another LED on. And you could see that it is turning different LEDs on. It means that this 7 segment is common anode. It is easy to remember because VCC is usually indicated with red, and the red probe is connected to this common pin which is a common anode, and the anode of the LED is connected to VCC. So this 7 segment is common anode. And when I connect both probes to common pins, again my multimeter beeps because they are connected internally. And different pins, different LEDs are on. I'm checking all the pins to make sure that all the segments are correct and all right. But the question is how to determine whether it is common cathode. To determine this, connect the black probe to one of the common pins, as I did here, and connect the red probe to different pins. You see, no LED is turned on, so it is not common cathode. If it was, the LEDs would be turned on like what happened previously. Discussing 7 segments is enough for now. Let's get down to business and prepare the circuit. Prepare the microcontroller and your bluepill and mount it on your breadboard. Make sure that the orientation is right and the pins related to ST link must be pointed upward so you could connect it to your laptop or PC easily. Then prepare your 7 segment and mount it on your breadboard. Again, make sure doing it in the right orientation. The dot must be placed in the right down corner. And now I'm going to connect pin A of 7 segment to A0 of bluepill and pin B to A1 and then pin C to A2, and generally pins A through G of 7 segment to pins A0 through A6 of the bluepill. This picture might be a good reference for you. By using decent resistors and connecting two push buttons to pins B6 and B7, your final circuit should look something like this. In fact, I've corrected the circuit. I've connected the common pin of the 7 segment to 3.3 volts via the 330 ohms resistor, and see that this line is connected to 3.3 volts via this red wire, and I've connected two push buttons to pin B6 and B7, and the other sides of the push buttons is connected to 3.3 volts. So when they are pressed, pins B6 and B7 are set to high. And as mentioned, the 7 segment pins are connected to pins A0 through A6 of the microcontroller. So let's configure our peripherals for the project using STM32 CubeMX. But before that, note that you could access my IOC or CubeMX files in my GitHub repository, or the source code and the source files, which is in main C, and generally the whole project in my GitHub repository, and the link is provided below in the description. Let's run STM32 CubeMX, access to my MCU selector, and I've already marked my microcontroller, which is STM32F103C86, so I click on it. And as always, the very first thing that you need to do is going to RCC and enabling high-speed clock with crystal ceramic resonator, and then go to System, Debug, and Serial Wire. And yeah, that's it. Then we need to set pin A0 through pin A6 to GPIO outputs. These pins are connected to our 7 segment. And here I made a mistake and I set pin PA7 to GPIO output, which is unnecessary, but as long as this pin is not connected to anything, it's okay and it doesn't bother us. And then it's time to selecting our inputs. Pin PB6 and PB7 were connected to our push buttons, so we set them as inputs. And if you want to see your alternatives for selecting this pin, you could click on this and pressing a control button, you would see your alternatives for selecting inputs, and yeah, that is how it shows you. But PB6 were okay, it was close to my push buttons, so I selected them, and PB6 and PB7 were connected to our push buttons. Then go to GPIO, we want to pull them down, and let's find our inputs. Oops, I've mistakenly set it to output, I've corrected it. Then pull down your inputs, so by default they are connected to ground. Then go to clock configuration. 8 MHz is, I don't like it, put it to 72 MHz, and that's the maximum clock frequency. In project manager, copy only the necessary library files and select a name for your projects. I chose 7 segment, you choose your own, and select a destination for saving your project. I did it for my own. And the preferred toolchain 90 is MDK ARM, which is keil microvision. Generate code, open project, So let's scroll down and find our main. And first of all, we are going to create an integer and name and displaying number. This will be the number that we are going to show it on our display and initialize it with number 0. And then we're going to create an array of 10 numbers that range from 0 to 9. And by the help of these numbers, we're going to select different segments of 7 segments for displaying number. For example, for displaying number 0, just part G must be off, and you could see that here. And note that alphabets in reverse order because we've connected segment A of 7 segment to PA0 and B to PA1 and so on. So for representing 0, we just set G to 0 and others to 1. And we want to find its hexadecimal format. So we copy this number, go to your calculator, make sure you're on programmer mode, and paste the number here. Oops! Make sure you're entering the number in binary format because this is binary. Paste your number, and hexadecimal format is 3F. It is in Persian. I write it here in English. Then for showing number 1, just pins B and C must be selected. And so we set these 1 and others to 0. Again, we go to the calculator and paste it there. And the hexadecimal format is 6. So I write 6 here, OX06. OX represents that it is a hexadecimal format number. For representing number 2, just pins F and C must be set to 0 and others must be set to 1. So we find its hexadecimal format again, and it is 5B. So we write it in the keil, OX5B. Just for the sake of beauty, let me change all the alphabets to capital letters. And do the same thing for numbers 4, 5, 6, and 7. And find the hexadecimal format and write it in the keil. And 4F is for number 3 and 4. Just do the same thing, 5, 6, 7, and number 8, which is really important because in this number we are selecting all the segments of the 7 segment, and we can use it further whenever we want to select all the segments, whether to turn them off or turn them on. So the hexadecimal format number, which is related to number 8, is shown here. We copy it, which is 7F. And for number 9, it's just enough to set E to 0 and find the corresponding hexadecimal format number. So the final array should look something like this. Let's scroll down, and before entering the while loop, initially we want the 7 segment to show number 0. First of all, we have to delete all the 7 segments that are on, and we have to turn them off because we want no footprints of the previous numbers to be shown on the 7 segment. So we use write pin function and we select all the segments which we discussed earlier, and by using the GPIO pin set we turn them off. Why set? Because LEDs are off when their cathodes are set to high and our 7 segment is common anode. It is a little bit tricky because for turning them off we have to use GPIO pin set, but you will get used to this. And then display our displaying number on the 7 segment GPIO A that we've dedicated to our outputs, and digits we use displaying number, which is 0 at the moment, and we turn it on by GPIO pin reset. Building our project, brilliant, 0 errors, 0 warnings. Let's scroll down to the while loop. we want the display number on the 7th segment increases whenever the push button which is connected to pin 7 is pressed. So if this push button was pressed, we have to do something. We use a read pin function to read the pin which is connected to push button which is connected to pin 7, and whenever it was pressed, increase the display number by 1. But what if the number reaches 10? If it happened, then set the display number to 0. In this manner, we are creating a loop for this. Then turn all the LEDs off. At the moment, we want to delete all the footprints of display number 0. We select all the segments by number 7F and turn all of them off by GPIO pin set. And then we're going to display our desired number on the 7th segment. We use write pin function, digits, and show the current display number, which is increased by 1 if the push button is pressed. And these instructions are done pretty fast, so we must provide a delay. For the microcontroller, 250 may be enough. Save the project, read it. 0 errors, 0 warnings. So what about if we want to decrease the display number on the 7th segment? So we've connected another push button to PV6. If PV6 was pressed, so we have to read it. If it was pressed, the display number must be decreased by 1. What if we reach -1? Then the display number must be set to 9. Again, we are creating a loop in this manner. Then delete or turn off all the segments that are on, and then display the current display number. It is so similar to what we've done before, so I copy and paste it to do this and add a delay for this again. And yeah, it's okay. Let's build a project. Brilliant. 0 errors, 0 warnings. So let's connect the ST-Link to my laptop. First, let's go to options for target. An output text file is created. Language C is C99. Great. In debug, go to settings. As you can see, the ST-Link is recognized successfully. Flash and download reset and run is checked, and pack enable is unchecked as expected, and it is what we want. So let's download the code to our microcontroller. And here is the final result of our project. By pressing the left side push button, it increases the display number by 1. On the other hand, by pressing the right push button, it decreases the display number by 1. So for now, you might think that what about displaying larger numbers or even displaying words and letters? A solution for this question and problem may be LCD, which is going to be our next project. Stay tuned. Good luck.